All right, guys, welcome to our lesson number 11 for finding limits. We're going to talk about finding limits of exponential and logarithms today. Once again, probably going to be making a lot of use of L'Hopital and concepts of infinity. So let's go ahead and take a look here. So let's review some basic facts, first of all, about exponential functions and logarithms. First of all, e to the 0 power equals 1, and natural log of 1 equals 0. So let's remember those facts. That'll be coming in handy for the lesson we'll be looking at today. So here's some basic facts about limits of exponential functions that we want to be aware of before we begin. The graph of the function e to the x looks like this. And so you guys can see here as x approaches infinity, so that means as I move in this direction here, the y value, which is the limit value we're addressing, is getting bigger and bigger and bigger. And so that's going to be infinity. So the limit of e to the x as x approaches infinity is going to be infinity. All right. Now, what if I'm approaching negative infinity, though? That means I'm going backwards on this thing. So as I go in a backwards direction, as you guys can see, it's becoming very flat. It's approaching a y value of 0. So if you're approaching negative infinity with e to the x, then it's 0. Now, here's probably a better way to write this down on your notes, just because it's how we're going to be looking at it on our papers today. So by direct substitution, we get this, and that's just going to be infinity. And then for this one, we're going to get e to the negative infinity, which is 0. And that's pretty much all you need to know. Now, if you want to have a little bit of fun here, I'll show you a little bit of math. As you guys know, when you have a negative exponent, that just means you put it on the bottom, right? And we talked about how e to the infinity is infinity. And anytime you have 1 over infinity, that's just 0, which is what we got here. So, but we don't need to do all that. That's just me showing you guys how all of the ideas we've learned so far are connecting together. Let's look at the last one here. Ln is an interesting looking function. Ln looks something like this. It has a vertical asymptote at the y-axis there. And as x goes into positive infinity, we're going to say that this goes to infinity as well. It just keeps going up higher and higher. Does it very slowly, but it does go up higher and higher. We're not going to have a approaching negative infinity, and that's because it can't approach negative infinity. It gets stuck at the vertical asymptote. And we'll talk about that maybe more on another day. But for now, we're not going to say that Ln can approach negative infinities because it just can't. The x value doesn't get to go that far. All right, so there's some nice little concepts that we want to be aware of. Once again, maybe we should write our answer maybe a little differently, just so it'll look more like what we're going to be doing in our actual work today. There you go. So that'll be what you want to have on your notes. You don't need the graphs or nothing. This is kind of the quick little reference that will be helpful. All right. So it's going to be a short lesson today. Not much to it. We're just going to do one example, one student practice, and that'll be it for the day. So let's pull up some sample problems that we'll look at. All right, so if I do direct substitution, I'm going to get Ln of infinity over 2 times infinity. And Ln of infinity, as we discussed on the last page, is infinity, and 2 times infinity is infinity. And Mr. Bailey committed the cardinal sin there. You're not supposed to have equals. So let's put an arrow. All right, and so therefore, by L'Hopital, because we have that special indeterminate form, we could say that the limit as x approaches infinity of Ln of x over 2x is equal to the limit as x approaches infinity of the derivative of these things. So the derivative of 2x is 2, and the derivative of Ln of x is 1 over x. As a general rule of thumb, it might be helpful for us to, simplify this. It's not horribly necessary, I'd say. You can maybe try it without simplifying first, but it's not too hard. I'm just going to go ahead and multiply the top and bottom by x there. And so what I end up with is I get the limit as x approaches infinity of 1 over 2x. And then if we do our direct substitution there, we're going to end up with, I'm running out of space, 1 over 2 times infinity, which is 1 over infinity. I'm going to use arrows here. And 1 over infinity is 0. So we end up with an actual answer here. Now, I feel safe using arrows here just because this is not really a number yet. You know, this is actually a weird mathematical expression, which probably is just helpful for us to write it, but not really technically correct to write it that way. So if you wanted to kind of avoid all that kind of stuff, what you could do is you could get rid of all these things here, and you could just put equals 0. Because it is true that this limit equals this limit by L'Hopital, and it's true that this limit is equal to this limit just by simplifying, and it's true that this limit actually equals 0. So here I'm comfortable with putting equal signs, but as soon as you start writing expressions with infinities and stuff, I would just use arrows. Okay, so let's go and take a look at another problem here. We're going to apply the limit to each of these pieces here on the inside just with direct substitution. And so we're going to end up with 2 e to the 0 minus e to the 0 over 0. And these cancel to make 0. So once again, we're just left with 0 over 0. No surprises there. So therefore, by L'Hopital, we have the following. We're going to go ahead and take the derivative of this whole thing here. So I guess I'll just write the original one first. Okay, so how do we take the derivative of this? Well, the 2 is going to act like a constant, so it's just going to stay there. When you take the derivative of this e to the x, you're going to get e to the x. Now, when you take the derivative of this one, you're going to get e to the negative x again. But since there's a negative, you have to do the chain rule. So the derivative of that exponent is -1. So we would put the -1 in the front here. But since there's already supposed to be a minus, that's a double negative, and basically what we're going to end up with there is a positive. And on the bottom, you end up with just 1. So then we go ahead and do our direct sub, and we end up with 2 times e to the 0 plus e to the 0, which is 2 times 1 plus 1, which is going to be 4 at the end. All right. Let's go ahead and take a look at another one. Okay, so let's go and do some direct sub. If I plug in 1 here and here, I'm going to end up with 2 times 1 minus 1 over ln of 1. And in both cases, that's a 0 over 0. So we have, by L'Hopital, the fact that the limit as x approaches 1 of this function is going to be equal to the limit as x approaches 1, or there's my constant, that'll stay. Then the derivative of that's going to be 2x, and the 1 just goes away. On the bottom, the derivative of ln of x squared. Well, the derivative of ln of x squared is going to be 1 over x squared times the derivative of that x squared, which is 2x. It's a chain rule, where this is kind of like an inside function. The derivative of ln x squared is 1 over x squared. That's the derivative of the outside. And the derivative of the inside is 2x. And then we multiply them together. Once again, it would probably help us out a little bit to simplify these. And to save myself some writing space, I'm just going to show my work here. But if you want to rewrite it on your notes a little bit. If I do 1 over x squared times 2x, the 2 is going to go on the top, and the x is going to cancel one of the x's off the bottom. And so basically, if I were to try to simplify this a little bit, it's going to end up being 2 over x. And then to simplify it a little bit more, I don't like that fraction on the bottom, so I'm going to multiply the top and the bottom by x to cancel that out. And what I'm going to end up with then as a result is I'm going to have the following. And we're ready to go ahead and just do some direct sub. So you're going to end up with 4 times 1 over 2, which is going to be just basically final answer. And one more before I let you guys practice. This one's at infinity. So if I do direct sub here, I'm going to have infinity over e to the 2 times infinity. Now, 2 times infinity is infinity, and e to the infinity is infinity. So we have a nice L'Hopital situation there. All right, the top of the derivative of the top there is 1. The derivative of the bottom, the chain rule, so the derivative of the outside function is just the same, e to the 2x, but the derivative of the inside, which is the exponent itself, is 2, so that's going to go there in the front. Then we're going to go ahead and do our direct sub again here. I'm going to have 1 over 2 times e to the 2 times infinity. And as we said before, 2 times infinity is infinity, and e to the infinity is infinity, and infinity times 2 is infinity, and when you have 1 over infinity, that's going to be 0. And so that limit would end up being 0. All right. So let me bring up a couple for you guys to try out. Okay, guys, so here you go. Go ahead and try out these 2 problems, see how you do. When you're all done, pause the video, and you will see the solutions. All right, so here's our solution set for that student practice. I didn't show the thing where direct substitution results in an indeterminate form, and I didn't write out the by L'Hopital's rule thing. Just kind of putting out what you would get after you applied L'Hopital's rule and then the final answer. So after applying L'Hopital's rule to this, you would end up with this new limit here. And direct substitution here, you end up with 1 over infinity, which is 0, over 1, which is just going to be 0. For number 6 over here, applying L'Hopital's rule, we end up with this as our derivative expression. Direct substitution ends up making infinity on the top, and 2 just stays on the bottom as is. And so we're left with infinity over 2 is just infinity. Number 7, doing L'Hopital's rule, the derivative causes the minus e to the negative x to become plus e to the negative x, because when you take the derivative of this, it puts another negative in the front, which makes it become positive. And the derivative of the bottom is 1. Direct substitution gives me e to the 0 plus e to the 0 over 1, which is 1 plus 1 over 1, which is 2. And then finally, for this guy here, we have a 2 in the front. So when you apply L'Hopital's rule, the 2 stays. The derivative of ln of x squared is 1 over x squared, and the derivative of the inside is 2x. The derivative of the bottom is also 2x, and I just went ahead and crossed off those 2 x's and multiplied the 2 to the top and got this. You might have simplified it in a different way, but you ultimately should have ended up with the same thing. And then direct substitution would give us just 2 as a final answer. And that's it. So that's limits with what do they call? I'm sorry, I'm having a brain gap here. Exponential functions and logarithmic functions. Anyway, that's it, and we'll talk to you guys later.